Greetings to all. My name is Narsingarao. I work in Oak Ridge National Laboratory in Computer Science and Mathematics Division. The title of our paper is Tiling Framework for Heterogeneous Computing of Matrix-Based Tiling Algorithms. In brief about our paper, so we are proposing a tiling framework with a tiling data structure for heterogeneous memory mapping and parameterization to heterogeneous task specification APIs. And we have integrated this framework in the Matrix, which is a math kernels library for heterogeneous computing using the Iris runtime. The main benefits of our tiling framework is that, okay, first it enables this tiling algorithms for heterogeneous computation, and it also improves the programmability of tiled algorithms. So you need less number of lines to write the tiling algorithms. And we also improve the performance by 20% when we actually compare with the traditional way of writing tiling algorithms, because when we write the traditional way, we don't actually utilize the 2D or 3D data transfer APIs, so which is even more tough to write such kind of APIs utilization. So yeah, and we also don't need the tile to flat and flat to tile conversion of the matrix tiles. So this leads us with the higher performance with our framework. Okay, so in the outline, so we first go through some brief background of Iris runtime and matrix libraries, and we'll see some state-of-the-art tiling approaches, and we will also go through our proposed tiling framework, and then we will go through with our some examples of the using tiling framework for tile matrix addition, multiplication, and LU factorization algorithms. And at the end, we will see some experimental results in terms of overhead of this tiling framework and performance gains achieved with this tiling framework. And at the end, we will see some conclusion and then future work of our tiling framework and some resources of using this tiling framework. Okay, so in brief about Iris runtime, so Iris is runtime is available in the public repository GitHub and also in our internal GitLab repository code.ornl.com. Okay, so what is this Iris runtime? So it is actually a runtime for heterogeneous computing, and it has the heterogeneous platform models, which where you can see the platform models of the multi-core CPUs, and also for the NVIDIA GPUs, and using the CUDA model, and AMD GPUs using the HIP, and then Hexagon DSP platform models as well. So it enables you to write the program using task-based programming, so where you create the tasks of the synchronous or asynchronous task and add dependencies among them, and you can even create a task graphs out of this task. And it has a heterogeneous memory model, so which handles the heterogeneous memory address space for the host data, host or application data objects, and this enables you to do some automatic data movement of this, transferring data from the host memory of the data object to the device memory of the data object. So, and you don't need to write this H to host to device and device to host data transfer commands in application. Iris runtime will automatically take care of it. And it also explores the different heterogeneous data transfer policies to see which data transfer policy is better, like device to device data transfer policy or host to device data transfer policies. And it can explore the if there are two CUDA GPUs, it can explore a direct data transfer from the CUDA GPU to another CUDA GPU. Okay, it has heterogeneous execution model as well, so which actually supports both static and dynamic task mapping policies, and also provides flexibility to write our own policy for the application and configure it in the Iris runtime. Okay. This is an example of using Iris runtime for the heterogeneous SAXP application. So where we are calling this SAXP call in the Iris runtime, where we can write the host code of this SAXP kernel call either using C++ or C or Python or Fortran. So an example C++ host code is given here. So here, okay, so if I see this, we are creating the host memory objects, and then we are creating the Iris memory objects, which are actually binding the host memory objects in this one, and then we are creating the tasks here. So by calling this saxp kernel inside. So now in order to call this saxp kernel, so we have provided different implementation of this saxp kernel uh, for the different device. Like for if it is for the OpenMP device, the like it's a multi-core CPU, so we will be using the OpenMP kernel to run it on the multi-core CPUs. And if it is NVIDIA GPUs, then we are written the kernels using the CUDA to run it on the NVIDIA GPUs. So yeah, and we can provide the kernels for the heap and to run it on the AMD GPUs, or OpenCL to run it on either on the NVIDIA or AMD GPUs together. So in this way, we can write the kernels for heterogeneous compute units, and Iris runtime will figure out at the runtime where to run this saxp kernel on what device with what programming language it has to choose. Yeah. Okay. Yeah. Now let's have some brief background on the matrix. So matrix is actually a combination of both Iris BLAS and Laris libraries. So Iris BLAS is having the heterogeneous math kernels implemented using the vendor specific libraries like OpenBLAS, MKL, and if it is for the NVIDIA GPU, it uses the cuBLAS, and if it is for the AMD GPUs, it uses the HeapBLAS. And so Iris BLAS provides unified APIs for the BLAS kernels, and the Laris is actually uses this Iris BLAS APIs to write the tiled algorithms for like the LU factorization using the Iris BLAS APIs, and applications can call these Laris APIs for the LU factorization functionality. So the algorithms of the LU factorization using tiled approach, it is a very configurable tiles where we can specify the what is tile size that we need. Then the Laris APIs will create the task graph with that corresponding tile size, and we can configure with the performance models and scheduling policies. And the matrix is which is actually published in 2 papers. One is in the SEEK workshop and the Iris BLAS in the HIPC conference, and it is available in the internal code code.ornl.gov GitLab repository. Okay, so let's go through some state-of-the-art tiling. So okay, we have the traditional approach, like where we can use the tiled algorithms using for loop iterators and loop indexes and loop increments. So it requires a lot of code you have to write, and it is error prone. So even a small mistake in the increment of the index, and that can actually lead to different kind of results in the task graph, which is very hard to debug as well. Okay, and there are some state-of-the-art domain-specific languages for this tiling algorithms, but most of them are actually for the homogeneous compute units. Some examples are like Halide and Tiramisu and Triton compilers, which actually have the facility to read these domain-specific languages and then convert the code into the compute unit-specific tiled algorithms. But these are not best for the heterogeneous compute units, for the reason that there are some challenges for this. One thing is that, okay, so how we actually manage the heterogeneous memories for these tiles, and then it should also provide some kind of a tiling utilities for creating these tiles and then map to these heterogeneous memories. And there is another challenge, like we need to create the task at the end using these tiles of the inputs and outputs, and at the same time it has to provide the ease of programmability, where we can write the tiled algorithms with a less number of lines and in a more representative way. And it also has to has to have the has to enable to use this device specific tile data transfer APIs as well, like the for the tile transfer from the host to CUDA GPU. Then it should be able to use this cuMemcopy 2D tile transfer APIs of the device. So what we need is a kind of tiling framework which will underneath handle all these challenges and provide a simplified APIs to the programmer, which will abstract all these and then uses the Iris runtime to provide the most optimized tiling algorithm. Okay, so this is our tiling framework. So we actually have the okay, the first thing in the tiling framework is we need to specify the tiles. So the tiling specification, like the size of the matrices in all dimensions, and size of tile, and the stride between tiles. So along with this, so we need to bind these tiles to the iris memory object. So in this case, we are dividing the matrix into tiles, and then these tiles are now also binded to some iris memory object for each tile, and where the iris memory object maintains the corresponding host tile information to device tile information. Okay, so it also enables the using this iris memory object for exploring this two-dimensional data transfers using device-specific memory transfer APIs like CUDA memcopy 2D kind of APIs. Okay, and the tiling framework also needs to provide some kind of iterators for the access of these tiles, either using the sequence iterators where you can access the tiles either in the row measure fashion, like the row after row, or the column measure fashion, like column after column. Okay, and in the case of three-dimensional tiles, then we have a three-dimensional like x, y, z, and which dimension will come first. So based on that, we can provide the sequence iterators, and there is some special sequence iterators we have provided, like row, column, or write down twice iterator, which is required for LU factorization. We will see this in the next slides. Okay, and some index-based iterators are required for random access of these tiles or interleaved access of these tiles for the algorithms like matrix multiplication. Okay, so this is tiling data structure in brief, where we have the tiling 2D 2D object, which actually has the aggregation of all the tile 2D objects. So where each tile is actually associated with the iris memory object. The tiling 2D object will be holding all the tile specification of the what is the stride of the tiles, and then tile size, and then the matrix size informations. Okay, and the same is actually for the three-dimensional tile, where you have the 3 dimensions of the tile under matrix information, and you have the association of the set of tiles with the binded with the iris memory object as well. Okay, so we have provided some iterators for the tiling data structure, like where you can see a simple row measure and column measure iterator by having these items member. So we can implement any number of iterators on this tiling data structure, and we can even configure these iterators. Like in our case, we can, by default we have the tile 2D row measure iterator, and you can configure it to the column measure iterator by simply parameterize to this items function. And if there are multiple iterators, we have to sequence, like in the case of matrix addition, where we need to iterate through A and B tiles simultaneously. So in this case, we can use some C++ range-based iterators on these multiple tile iterators together. So and you can access the A tile and B tile together and do the operation on these tiles. And index-based iterators, where you can where you can access the tile counts and then index of the tile, and then based on that you can actually access the corresponding tile at that index. Okay, so some example of the tiling algorithms using these iterators and data structures, like matrix addition using sequence iterator, so which is using range-based iterators of A, B, C tiles. And we are creating the task, we are adding this task to the graph. At the end, we are submitting the graph for the execution using the iris runtime. And then another example is a tiled LU factorization. So where we need a different kind of iterator, like we call that as write down or a row column iterator. So we are having the row measure first and then the column measure, and then we will go to next level for the next row and then next column. So it actually requires two level of iterators. The first level of iterator will be operating at the level for each level in the row, followed by column, and then we are applying the get array functionality, and then we need to apply the gem operation as well in that level. So for that one we are using the another level of iterator. So this will be a sequence iterator, but it would be configurable to set from which point we have to start. Like we have to start from this level 0, level 1, level 2, like that. Okay, and then using this simplified tiled algorithm, now we can create the task graphs of the LU factorization, so which is achieved with the less number of lines of the code. Okay, and the another example of is a tiled matrix multiplication using tiling framework. So this actually utilizes the index-based iterators, because we need to access the A, B, C tiles based on their indexes. So in this case, we are iterating through the number of row tile count and column tile counts of A and B, and based on the index of A and B tiles, we are accessing the C tile, and then we are applying matrix multiplication operation on top of it. If we observe this in our tiling algorithm, so we have the number of lines reduction is more than some 45% to 78% compared to traditional way of writing the tiling algorithm for the gem and LU factorization. Okay, so when we see the overhead of our tiling framework, so the overhead is considered like the time taken to create this heterogeneous task and task graph, either using the traditional way or our tiling framework. And we have observed that the overhead is actually 90 microseconds, which is actually not varying much when we vary the size of the tiles for this LU factorization task and the descent tasks. Okay, so this is more this is actually very negligible, this 90 microsecond, which is actually very much equal to very carefully handwritten tiling algorithm. Okay, and the performance enhancement with the native tile data transfer APIs. Okay, so when we compare with the tiling, the traditional approach, where it is very hard to write the code with the native tile data transfer APIs, because that is actually runtime specific feature, so we cannot write it ourselves. Okay, and okay, when compared to traditional approach, we have observed the gains of some 28% approximately, 20% approximately performance uplift when compared to traditional approach. For this experiment, we have actually varied the matrix size of the different sizes to understand the performance gains. Okay, in conclusion, yes, we have proposed this novel framework for tile algorithm and heterogeneous computing, which is very unique for and required for this heterogeneous computing need. And our tiling framework can create tiles, binds the tiles to the iris memory objects, and handles the heterogeneous memory objects through runtime, iris runtime, and it enables you to create heterogeneous tasks for heterogeneous computing very easily. And the benefits, as we have seen, it simplifies the tiling algorithms, and then it is also performance efficient, and also overhead is very less when compared to the traditional approach as well. And it also exploits this architecture native data transfer APIs as well. And the future work is that we can further make it more simplified by having some domain specific language for these tiling algorithms. And you can find our resource of matrix and iris in the internal core GitLab repository. You may need some XCAMS ID, which you can register it through this website, and you can contact us for any help that you need it. Thank you very much.